Valence bond and molecular orbital theory is something that you will spend a lot more time in college chemistry. In this video, I'm going to briefly explain what hybridization is and how to recognize the hybridization for each of the electron pair arrangement. The valence bond theory or atomic orbital theory explains the overlapping of orbitals. The overlapping of orbitals prevents distinct orbitals from showing by themselves. So you will not see a s orbital as a sphere. You will not see a p orbital as a dumbbell. But together they will be hybridized. And this mixing of atomic orbitals create new orbitals of equal energy. New hybridized orbitals are called degenerate orbitals. So hybridization is when you take one, such as an orange and a tangerine, and make a new fruit called a tangelo. So here we are taking s and a s orbital, mixing them together, a s and a p orbital, mixing them together, a p and a p orbital and mixing them together, or a spd mixing them together. And these mixtures will create new orbitals. These new orbitals are called degenerate orbitals. These are examples of pure orbitals. They are mixed together to produce hybridized orbitals. So, an s orbital looks like a sphere. If I mix an s and s orbital, it looks like a ring. If I mix a s and a p orbital, an s is a sphere, a p is a dumbbell, a hybridized sp orbital in which one end of the dumbbell will be really tiny and the other end will be much larger. If I mix a s and a p, because p's can go into x, y, z, it will produce sp3, 3 orbitals that are sp3, in which one lobe is going to be really large and the other lobe is going to be really small. So these are hybridized orbitals, and this is what they look like. You will not be required to draw these. You just need to understand what hybridization means. When we account for hybridization, we look at the electron pair arrangement and not the molecular structure. As we stated before, a single, a double, a triple, and a lone pair counts as one. From quantum numbers, in order to have a p orbital, you must have an s orbital first. In order to have a d orbital, you must have 3 p orbitals first. So we're going to fill in that order. The s is going to be filled first. And since there is only one s, we only have one s. The p orbital, we must fill 3 because p has 3 orbitals in the x, y, z. D has 5 orbitals, but we only go up to 2 because we do not have elements that we know of that exceed that. Electron pair arrangement that is linear has 2 bonds, 0 lone. So we must have an s first and then a p, sp. Trigonoplanar electron pair arrangement is 3. You could have 3 bonds, 0 lone, that adds up to 3, or you could have 2 bonds and 1 lone pair, and it also adds up to 3. So you must have an s and then a p and p. That's 3, sp2. Tetrahedral is 4. You could have 4 bonds, 0 lones. You could have 3 bonds, 1 lone. You could have 2 bonds and 2 lones. Whichever one you do, The electron pair arrangement is tetrahedral because it adds up to 4. So we must have an S first and 3 P's. So this is sp3 because P has 3 orbitals. When I add the S and the 3 P's, that is 4. Trigonal bipyramidal is 5. Whether we do 5 bonds and 0 lone, 4 bonds and 1 lone, 3 bonds and 2 lones, 2 bonds and 3 lones, they all add up to 5. So the electron pair arrangement is trigonal bipyramidal. So the S is 1. There's 3 P's. And since all the P's and the S are filled, we need to go to D, and that's 5. Octahedral has 6 bonds and 0 lone pairs, or 5 bonds and 1 lone, or 4 bonds and 2 lones. They all add up to 6, so this is octahedral. So we need to fill the S first, and then 3 P's, and then I need 2 D's to get 6. We look at the electron pair arrangement. If I have linear and there's 2 sp, so we know the hybridization is going to be a sp hybridization, which will look like this. Trignoplanar is sp2 because it has 3. In addition, valence bond theory also gives you sigma bonds and pi bonds. Sigma bonds are single bonds. This is the symbol for sigma. It is from hybridized orbitals. Pi bonds, this is the symbol for pi, are double and triple bonds, and these are formed by unhybridized orbitals. You must always have a single bond before you can have a pi bond. So every bond must start with a single bond. So a single bond here will have a sigma bond. A double bond will have a sigma bond first, and then the second bond will be a pi bond. A triple bond, again, will start with a sigma bond, and then the next 2 will be pi bonds. So a triple bond will have 1 sigma bond and 2 pi bonds. So a sigma bond is hybridized. So we could take an s orbital and another s orbital and hybridize them. So you have an ss bond. You could have 2 p bonds and hybridize them. So it's a pp bond. Or we could have a s and we could have a p, and then they will make a sp bond. A pi bond is unhybridized. It is overlapping of p orbitals. P orbitals look like a dumbbell. So if this is one element and then we have another element next to it, what they do is these 2 will overlap, and it'll be like this, something like this picture right here. In this picture, we have 2 pi bonds. We have pi bonds that are overlapping this way vertically, and then we have pi bonds going into the z direction. So this is the first pi bond and this is the second pi bond. So the picture on the right is a triple bond because, again, sigma bonds must exist first. You have 2 pi's. So the sigma bonds, if it was drawn, will look like this between the 2 pi bonds. Determine the number of sigma and pi bonds for the following structure. As stated in class, if we have CH3 and the H's are next to C, that means they are bonded to the carbon. So I'm going to redraw the structure. So we have a hydrogen, 3 of them, surrounding carbon. It is bonded to a carbon here, which is bonded to a hydrogen, and on top there is a carbon and 3 hydrogens. This carbon is now bonded to another carbon with with hydrogens on opposite side, and this carbon right here is bonded to the last carbon, and the last carbon has hydrogens surrounding it. Since these are all single bonds, these are all sigma bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 sigma bonds. If I draw the second structure, it has 5 single bonds. So this is 1, 2, 3, 4, 5 single bonds. So it has 5 sigma bonds plus another sigma bond right here. The first bond is a sigma. So this one has 6 sigma bonds and 2 pi bonds, because this is a triple bond. In a triple bond, the first bond is a single bond, so it has to be a sigma. The last 2 are pi bonds. So this has 6 sigma, 2 pi. Bottom left corner, if we have a structure that is drawn in this format, in the middle there is a carbon. So that means we have a carbon which is bonded to an oxygen and a hydrogen, a single bond here, to another hydrogen, to another oxygen which is bonded to 2 hydrogens. Everything here again fills the octet rule, so we could put the lone pairs in for the oxygen. Since the oxygen on the right already has 2 hydrogen and is bonded to the carbon, it only needs a pair of electrons. In this picture too, everything is a single bond, so they are all sigma bonds. So 1, 2, 3, 4, 5, 6, 7. There are 7 sigma bonds. In the last picture, if we redraw it, if it's not written, this is carbon, which has a double bond to an oxygen, to a single bond, and another single bond, hydrogen. The oxygen needs 2 pairs of electrons to fulfill the octet rule. This picture has 3 sigma bonds and 1 pi bond. The sigma bond is 1, 2, 3, and then the pi bond is the other double bond. If I have a double bond, the first one is a sigma bond, the second one is a pi bond. You need to understand how the pi bonds are formed due to overlapping of p orbitals in this picture. And in order to have a pi bond, you must always have a sigma bond first. You need to understand sigma bonds are always single bonds. A double bond has a sigma and a pi. A triple bond has a sigma and 2 pi's. And when you are doing the hybridization, count the total electron pair arrangement. Just fill them up in order. S has 1 orbital, P has 3 orbital, D will have 5, but we will only go up to 2. And remember, the S must be filled first, then the P's, then the D's. It just has to add up to the number of bonds plus lone pairs. So if it's linear, it's 2, so 1 S, 1 P. If it's trigonoplanar, we need a S and then 2 P's because it has 3 bonds, or sp2, and so forth.